the integral of cosine square root of x dx from 0 to pi over 2. So the problem with this is that we don't have a substitution problem set up for us. We have to force it into a substitution problem. I can't use substitution. I could potentially use by parts, but I don't have a substitution problem. So, and by parts is difficult because with by parts, as we know from a previous section, we ended up with that cycle that would end up from sine to cosine, and we'd have to try to end up with something on both sides. So instead, I'm going to use my knowledge of identities to force this into a problem that is workable, similar to what I did on the previous example. Except now I'm going to say that this is cosine x cosine square root of x dx. And the reason I'm going to do that is because then this becomes cosine of x 1 minus sine square root of x. So now I've introduced a sine. Right there. Introduce myself a sine. That sine, when combined with this cosine, will make a very nice substitution problem. Whereas when I multiply cosine times 1, that's just going to be the integral of cosine. And that's an easy one. So this is going to be 0 to pi over 2 cosine of x minus cosine of x sine square root of x dx. And that u equals, with this one, I'm going to break it up into two pieces. Let me draw that out in case that's not clear. So this is going to be cosine of x, which is easy. And this is cosine of x sine square root of x dx. So I only really need a substitution for this guy. This is just going to be sine. No problem there. So with this one, I'm going to get u is equal to sine, not square root of x, just sine of x. So that du is going to be cosine of x dx. So that and that become my du. Zoom out a little bit. And then that's going to be sine of x from 0 to pi over 2 minus the integral from 0 to pi over 2 of u squared du. This guy right here is going to be 1 minus 0, so that's going to be 1. But this guy is going to be u to the third over 3, and since u is sine of x, it's going to be 1/3 sine of x to the third from 0 to pi over 2. And that's going to be 1 minus, this is going to be 1 minus 0 times 1/3 is 1/3. 2/3. So using that identity there, it made it into a very solvable problem. Whereas before, we were stuck with this cube of x, cube cosine of x, and we weren't quite sure what to do with it. So to recap, if you have the integral of sine n x dx, or the integral of cosine n x dx, or the integral of them combined with different or the same, doesn't really matter, powers, as if n or m are odd, or both, still works, okay, then what you can do is step 1, manipulate using sine square root of x plus cosine square root of x equals 1. And then 2, make u sub, and then 3, integrate. So that's what you can do if you're dealing with some kind of an odd power. So your next question should be, what the heck do we do when it's even? Great, I know what to do as long as one of them is odd, super, but you're going to put a fourth power on the test, and what do I do then? Right? That should be your next question. So we're going to start small. We're going to start with squareds next. Okay, we're going to go ahead and find the integral next of sine squared of theta d theta. So in general, with these squared versions, because we're going to do a cosine, what we really want to do is we want to use our knowledge of double angles to change this squared sign, which is difficult to integrate with current methods, and instead focus on making it into a double angle with this identity. We know that sine squared of theta equals 1/2 1 minus cosine of theta, 2 theta, double angle. So that means I can go ahead and change this to be 1/2. This is the integral of 1 d theta minus the integral of cosine 2 theta d theta. And that's going to be 1/2. The integral of d theta is just theta. And the integral of cosine 2 theta, to do that, we have to say that u is equal to 2 theta in a room. To theta, so that du is equal to 2d theta, so that 1/2 du is equal to d theta. So now this becomes cosine of u du, which is going to be sine u du, or excuse me, sine of u. So then that minus sine, and instead of u, I'm going to put d theta directly, 2 theta in. And then I can't forget this 1/2 right here. So that answer is going to be 1/2 theta minus 1/4 sine of 2 theta plus c. And likewise, you can integrate it on your own, the integral of cosine. So what you can do is you can go ahead and pause the video here, see if you can figure out cosine squared of theta based on the same process to get that practice. And I'll do it here. It's going to be 1/2 the integral of d theta plus, because that's how the identities differ, cosine of 2 theta, integral of d theta. And then when I sub out the u for 2 theta, again, that's going to be equal to 1/2 theta plus sine of 2 theta, 1/2. So that's equal to 1/2 theta plus 1/4 sine of 2 theta plus c. Now we can take this one step further and take these two integrals we have. Let me go to the next. So I know that the integral of sine squared of theta d theta is 1/2 theta minus 1/4 sine of 2 theta plus c. Well, if I use the double angle identity for sine, I also get that that's 1/2 theta. And sine of 2 theta is 2 sine theta cosine theta. When I mix that 2 with that 1/4, I get 1/2 sine theta cosine theta plus c. and the integral of cosine squared of theta d theta, which is 1/2 theta, plus 1/4 sine double angle. I can change that to be 1/2 theta plus, and again, sine of 2 theta is 2 sine theta cosine theta. And I'm going to mix that 2 with the quarter right here to make 1/2. So 1/2 sine theta cosine theta plus c. So these would be really handy integrals to memorize at this point, because while they're not very hard to derive, they are they're not very hard to derive, that they do take a little bit of time and you have to know what you're doing. So it'd be a handy thing to have these memorized, because as we see quickly here, we're going to get into integrals where this is what it boils down to. So now, let's see if we can use this. Okay, so we're